recall, this is what we started talking about last time. We have quadratic form, q, abc, and we attach to it the root a sub q. This is a complex number, so let's say the discriminant d is the discriminant, b squared minus 4ac, and let's say it's negative. Okay, so q is definite. Either positive definite or negative definite, right? So this number a, alpha was negative b plus or minus, let's take the plus in the upper half plane, square root of the discriminant over 2a. So this is in the upper half plane inside the complex plane. Right? You guys remember this? Yes, I hope. And we observed that when we change q to q1, or let's say q2, so this is the root of q, thought of as a quadratic polynomial. Setting y equals 1. Okay? And studying these things will make it easier for us to understand how to study quadratic forms. It'll kind of, you can do this purely on the level of quadratic forms, but actually I hope you saw last time that you can do things much more simply on the level of these. So let's see what's going on. So let's prove a theorem. If q2 is q1 composed with gamma, okay, so q2 and q1 are equivalent. That is, q2 is equivalent to q1, and we said that that's an equivalence relation. So here I mean that gamma is in SL2Z. Then alpha of q2 is equal to something acting on alpha of q1. So this is what we started working through last time, and I believe we didn't finish. Is that correct? Okay. Right. And let's remember what q2 is in terms of, so q2. So this is a proof. We don't know what the theorem is going to state yet, but we will in a second. Well, let me tell you what it's going to be. It's not that hard to figure out what it's going to be. I think it's going to be gamma inverse. Okay, so this is my claim. I claim that gamma inverse. Now, remember what this means. This means the fractional linear transformation. This is a fractional linear transformation. Okay, so the thing that we have to prove, so let's start with gamma inverse fractional linear transformation acting on alpha of q1. Do we need to do an explicit example, or you guys understand what all the algebra that we're trying to compute is trying to do? Can you write in keep going or explicit example? Keep going. Okay. At least one more person. Keep going. Okay, great. So let's start with this. So what is this? Gamma inverse, we remember what gamma inverse is. If you have ABCD, so if gamma is ABCD, then gamma inverse, you flip the diagonal entries, negate the off diagonal, and divide by the determinant, but we assume the determinant is 1. Okay, so that's this acting on the complex number a q1, which is negative b1 plus square root of d1, but last time we proved that the discriminants of equivalent forms are equal, so I don't have to say which d, it's the same, over 2a1. Okay? So far so good? Continuing the calculation. What is the fractional linear transformation? If you remember what we do, we multiply d times alpha, add the b part is minus b, so that's linear on top, it's linear on bottom also, and it's a fractional linear transformation, so now we have negative c times negative b1 plus root d over 2a1 plus a. Does everyone follow all of this computation? All right. What am I going to do? Well, one thing I can do immediately is multiply the top and bottom by 2a1, so I already have fractions on top of fractions. Let's multiply through by 2a1. So if I multiply through by 2a1 here, and I multiply through by 2a1 on the bottom as well. So all I did is multiply top and bottom by 2a1. Is everybody happy with that? Now, how can I simplify this? This is why we spend all this time in grade school. If we have a square root in the denominator, it looks kind of nasty. We want to put it in the numerator. I should multiply by the Galois conjugate, exactly. The Galois conjugate, which because d is negative, is the complex conjugate also. So I'm going to multiply top and bottom of this thing by, let's see, I have a negative, this is a little c. We have to keep it's a good thing we have subscripts. We have subscripts d, there's no ambiguity about capital D and lowercase d. C is the one we have to worry about. So if you see a c without a 1, that means little c. Actually, there's no c's anyway because c is sucked into d. The discriminant is capturing all of the c's, and alpha only involves a's, b's, and d's. Okay, so if you see a c, it means lowercase c. Definitely if it doesn't have c1 in it. All right. So what do we have? So what is the conjugate? So we have to multiply this out a little bit to see what the conjugate is. First of all, there's this thing which is real, 2a1. It's going to be the same on top and bottom. Then there's a plus b1c plus cb1. Now here's the thing that needs a complex conjugate. There's a minus c root d. So instead of a minus c root d, I'm going to write plus little c root d. And I'm going to multiply that on top and on bottom. Does everyone see how I got this thing as the conjugate of this that we're multiplying on top and bottom to clear that square root of d? Can I see a thumbs up if you're following the calculation, or just type I'm confused or I'm happy? Happy or confused? Thumbs up. Okay. So let's take 5 minutes. What conjugate did you call this? This is a complex conjugate, but because d is now negative, so its square root is imaginary, so it really is the complex conjugate. There's something else you do in the indefinite case when d is real, but it's actually the same thing. It's just you replace the square root d by negative square root d, and that's the Galois conjugate. So Galois, Évariste Galois, G-A-L, this is Galois conjugate, is a way of thinking about roots of polynomials all together and the group of automorphisms of the set of roots of polynomials. We'll get to that not this semester, another semester when you take Galois theory. You'll see. Okay, now you see me, now you see the computation, right?
Well, your video is very, what do I say? Your connection's bad on your video, but your docam's fine.
All right. In the meantime, have you guys already finished the computation? Should I catch up to you? More messages below. More messages below. Okay, now you see me. Dependra is still typing. Okay, we get to compute. You guys want to take 5 minutes and do it on your own? All right, take 5 minutes.
Is it supposed to be very messy?
It's going to start out being very messy, and then all kinds of miracles are going to happen. So I can point to one miracle already. Well, let me not. Let's watch the miracles happen. If we've done this right, if gamma inverse really is the right thing here, then miracles are going to start happening. Am I hearing something? Can you just type if you're working? Can you type working into the chat so that I know everybody's on and the computer hasn't crashed again? Okay, so what's the upshot? The upshot is we proved this theorem that if two quadratic forms are equivalent, then what you can do is look at the action, the fractional linear transformation of the inverse matrix that makes them equivalent, and that is what will take the root of one to the root of the other. Okay, that's what this whole big calculation has told us. Well, now something magical happens, because now there's a way of reducing. So this is a geometric reduction algorithm. So give me some alpha, and I'm going to make it the simplest possible alpha. So this is an alpha in the upper half plane. Okay? Somebody give me a real part and an imaginary part. And I'm going to show you by example how the reduction process goes. One plus w. All right, that's going to be a little too simple, but I think you'll see the point anyway. 1 plus w, where is that? W is here. 1 plus w is here. It's already reduced. There's nothing to do. Give me something a little bit more complicated. How about a quarter plus, how about 3 plus a quarter I? 3 plus a quarter I. I just made this up. I have no idea what's going to happen to this number. All right, 3 plus a quarter I. Here's my upper half plane sitting inside the complex plane. 3 is 1, 2, 3. And a quarter I, this is I. So this is half I, this is a quarter I. A quarter I is over here. This is my point alpha. Okay? And I'm going to keep moving this point alpha until it's as simple as possible. So here are two matrices in SL2Z. So notice, observe, note, I'll call this one T, the translation matrix. This is in SL2Z. And notice it's usually called S. I call it the flip matrix. This is also in SL2Z. And let's see what these matrices do as fractional linear transformations. So T, if I have any alpha, what does T do when it acts on alpha? Let's check our understanding of fractional linear transformations. This means 1, 1, 0, 1 acting on alpha. So that's, remember what you do, it's A times alpha plus B over C times alpha plus D. So it's A times alpha plus B over C times alpha plus D. So you stick the 1, 1, 0, 1 into this formula. Okay? There's a 0 alpha, that's gone. Dividing by 1 doesn't do anything, and I just have on top alpha plus 1. So this is the translation matrix. It's the matrix that takes an alpha and shifts it, adds 1 to the real part, shifts it by 1. So what would I want to do to this one to make it simpler? Actually, now I do know exactly what's going to happen to it, but you'll see in a second. Well, to make things simpler, we could reduce the real part. We could reduce the real part down as low as possible. Okay? So simplification step 1. So simplification, reduction algorithm. Reduction algorithm. Algorithm, yeah, that's pretty close to English. Reduction algorithm, step 1. Use T, or T inverse. By the way, what is T inverse? I need to change the diagonal entries. The determinant is definitely 1. And negate the off-diagonal entries. Oh, right. Instead of shifting by +1, I shift by -1. Okay? Use T or T inverse to make real part of alpha. Well, what could I do? What's the simplest I could make it? If I'm allowed to shift by 1, yeah, I could make it between 0 and 1. There's a sense in which it's even simpler in this. You're absolutely right that 0, 1 is a perfectly good fundamental domain for the action of T. I could make it, if I center the interval at 0, to make it the real part between -0.5 and 0.5. Okay? To make the real part less than 0.5 in absolute value. Okay? So let's do that here. If I apply T inverse alpha is here at 2 plus 1/4, and T to the -2 alpha is here at 1 plus 1/4, and T to the -3 alpha has taken all 3 of these real parts off, and now we're at 1/4 I. Okay? Once you're inside this region, it no longer makes sense to do more of this because you're not going to make it simpler. But you have this other matrix, S. Step 2. What does S do? Let's work out what S does. S, composed with alpha, or not composed, but the fractional linear transformation of S on alpha. So this is 0 times alpha plus 1 over -1 times alpha plus 0. I'm putting the 0, 1, -1, 0 into this thing. So what is that? There's 0 of this and 0 of that. This is -1 over alpha. Also known as, if I multiply top and bottom by alpha bar, negative alpha bar over norm alpha squared. So what does this do? Well, in the case of, so this number is 1/4 I. So what is S? Let's work out what S of 1/4 I is. Okay, so -1 over 1/4 I. So, well, what does this simplify to? Why don't you write it in? 4i, exactly, 4i. So what this does is it sends 1/4 I up here to 4i. I don't have room to make 4i. 4i is up here. If this is I, then this is 2, 3, 4i. And so this is S of T to the -3 alpha. Ah, you can't see. There, now you can see. S of T to the -3 alpha is up here at 4i. So step 2 is, so what is this? What is the action of S? The action of S, I claim, changes whether you're inside the unit circle or outside the unit circle, because it replaces something of absolute value alpha by something of absolute value 1 over alpha. So absolute value of S of alpha is 1 over absolute value of alpha. So what it actually does is it flips you outside the unit circle. It changes your absolute value sign. Does everybody see that? So step 2 is use S to get outside the unit circle. And then if need be, and then just continue this. Continue this over and over again until you can't continue it anymore. Let's do another example. Sheik. What is real part of alpha? The real part. This is real part. T is a translation, so all T can do is change the real part. What S does, if you're not outside the unit circle, S does something very interesting, Debendro. When it stops, we keep getting the same root. When it stops is when you neither want to do this nor this. It stops when neither of these things change, make it simpler. None of these things reduce things. None of these moves reduce alpha. Give me another alpha. Let's do another example. So another example. Because I do have to give you the quiz problem. Yeah, 3 plus 5i, the problem with 3 plus 5i, if we're here at 3 plus 5i, we're just going to translate by 3 and then we're outside the unit circle. So that's why I knew I wanted something with a low imaginary part, but I also don't want an integer part here. So let's do, I don't know, 3 1/3. Yeah, 3 1/2. Okay, 3 1/2. Let's do 3 1/3, just to make it slightly more challenging. Plus, fine, a half I. A half I. Okay? Let's see how we can reduce this. So again, geometrically, we're here. 1, 2, 3. 1, 2, 3, 4. This is the real part. This is the imaginary part. We're in the upper part of the complex plane. So 3 1/2 is right here. This is 3.5. 3 1/3 is right here. That's 3 1/3. I forgot what we were doing. And then a half I, well, let's say this is I. So a half I is right about there. So here's my point alpha. Is everybody following? So I want to reduce this. Can I reduce it by using T or T inverse? Can I make the real part more simple? Yes. So if I apply T inverse once, twice, 3 times, I get the point t to the minus 3 acting on alpha, which is, I've killed off this 3. So that's a third plus a half I. Okay? Let's call this number, I don't know, alpha 1. Okay? The question is, do I want to use S2 or not? Is this number inside the unit circle or outside the unit circle? So let me draw the unit circle here. Let me draw the unit circle. And let's notice that the real part is between minus a half and a half. Here's a half, and here's minus a half. So I want the real part between minus a half and a half, and I want to get outside the unit circle. So here's alpha 1. Alpha 1, the absolute value of alpha 1 is a third squared plus a half squared, or the square of the absolute value of alpha 1. A third squared is a ninth, a half squared is a quarter, and a ninth and a quarter do not add up to more than 1. So it is advantageous to apply S. Who's totally, utterly lost? Can you write lost into the chat if you have no idea what I'm doing? Lost. Thank you, Sheik. Can I rely on you to can you unmute yourself and we can try to talk through it? Oh, I see. You have to come out and come back in. There you are.
Yeah, so how do we get alpha 1? And why do we have to multiply it by t cubed?
Okay.
Just jump backwards.
Yes. So the action of t, what t does is it shifts alpha by adding 1. It shifts it by 1 to the right. So what t inverse does is it shifts it by 1 to the left. It undoes t.
Oh, okay.
That's what this t inverse element is. So when I write t to the minus 3, what I really mean is apply t inverse 3 times.
Okay.
So this is t inverse once.
3 steps.
Yep, we did 3 steps of t inverse, and that made the 3 and a third. That cut the 3 off, and now we have just a 1/3. So we got the real part between minus a half and a half. We're happy as far as step 1 is concerned.
Okay.
Now the question is, are we also happy as far as step 2 is concerned? Have we gotten the number outside the unit circle? And the answer is this new number, which I'm calling alpha 1, just so I don't have to write t to minus 3 of alpha every time. It's inside the unit circle. So I do want to use s on it.
Oh, yeah.
So Sheik, what is s of alpha 1? Let's work through this together.
S
So s of anything is negative 1 over that something. So this is negative 1 over a third plus a half I.
yeah.
And now how am I going to figure out what this is?
We multiply it by its conjugate.
Perfect.
1/3 minus half I.
Perfect. Okay. So what do I get on top? I get a minus a third.
Plus half I.
Minus a third plus a half I. But all of that gets divided by a ninth plus a quarter. What's a ninth plus a quarter? 4 plus 9 is 13 36ths. Is that the denominator? So dividing by 13 36 is the same as multiplying by 36 13ths. So I get negative a third plus a half I times 36 13ths. Okay, so where is that? Well, let's simplify this a little bit. So the real part of this is, I guess I get negative 36 39ths, negative 36 39ths, and then plus,
18 over 2.
yeah, exactly, good, 18 13ths I. So we're almost done. This is actually pretty good. We're almost done. 18 13, so negative 39, 36 39ths is close to negative 1. Negative 1 is here. And then we're at a height just above 1. So I guess this new number, let's call it alpha 2. Alpha 2 is right about here. It has real part close to negative 1, and it has imaginary part bigger than 1.
So my question to you is that why do we want a point outside the unit circle? What's the use of that?
Yes, I haven't explained to you why that makes it simpler. The act, what I'm about to say, I'm rushing the presentation a little bit because we had all these technical difficulties. What people realized is that if you can get the point into this region, that is the simplest possible point, and that's also the simplest possible, that's the reduction theory of the quadratic forms. Okay, and the reason you can always do this is when you change the real part, you don't change the imaginary part, and if you end up inside the unit circle, then when you invert, you always increase the imaginary part. Look at what happened to the imaginary part. It went from a half, this was a half, to 18 13ths.
Yeah.
So I claim that in the upper half plane, inverting through the unit circle always increases the imaginary part, and that's kind of almost obvious by a picture. So really what happens is inversions, well, do you guys know about circle inversions? Have we ever talked about circle inversions? An inversion through a circle is you just draw a radial line, and then if this distance was, I don't know, well, I know what it is. This distance was 13/36. Then this distance is 36/13. So it's just 1 over. Inverting through the unit circle means draw a radial line and take the same point on the same at the same slope, at the same angle, but whose length is 1 over the original length. So if this length is 13/36, this length is 36/13. Right? We've changed the length to be 1 over. Now what S actually does, because that action reverses orientation, what S actually does is it does this flip and then it does a second flip across the imaginary line. That's what this minus sign is doing. So that's why alpha 2 wound up over here. Okay, so those two flips together are orientation preserving, and that's the action of S. The action of S is flip outside the unit circle. That increases the Y part, and then it flips again just because that's how orientation preserving actions work. So, Sheik, are we done? Are we inside this beautiful region, this most reduced region?
Not yet.
Not yet? What should we do?
We need to flip it once more.
Well, if we flip it, we wind up inside the unit circle, because right now we're outside the unit circle. We can shift it, exactly. First, we always want to shift it. We always want to use step 1 first. So we can shift it by 1. So what happens if I apply t to alpha 2? That shifts it to the right by 1. And if I add 1 to this, I get yes. If I add 39/39ths,
3 over.
perfect. 3 over 39 plus 18/13 I. Here's 3 over 39 is pretty close to 0, plus 18/13 I is above 1. So here is the final place. Now what did we do? We applied we applied t to the minus t inverse 3 times, then an s, then a t to alpha to get us the most reduced form of alpha that's inside this fundamental region. Yes. Let's do this once more, but now for quadratic forms. Okay? Sheik, can I, this is kind of working for me. Can I keep bothering you? Do you mind?
Yeah.
You mind being the guinea pig? Great.
Oh yeah.
All right, you're my guinea pig. So now the idea is reduce quadratic forms by reducing their alpha.
Can you bring it up?
Sorry, thank you. All right, so give me a Q. I'm going to reduce your Q. Give me some weird large Q. Not too large. We're going to do all these computations by hand.
Can I give you something in terms of mega?
So what I mean now is give me a binary quadratic form. So give me 3 whole numbers, 3 integers, positive, negative, with negative discriminant, if you would.
Can we have the whole one minus 7?
Sure. What was it? 7 minus 11, 15? 7 minus 11, 5? Is that the one? Am I remembering that right? And its discriminant, let's make sure we're good. The discriminant is 121 minus, yes, it's negative. What is it, minus 19?
Minus 19 is, yeah.
Right? 4, this is 20, this is 140. 140 minus 121 is 19. Good. And then alpha, its root alpha is negative b plus square root of 19i all over 2a.
Yeah.
All right. So is this already reduced or is it not already reduced? Well, it's not, okay, I was going to say it's hard to tell, but let's draw where it is. So the real part is 11/14. Is that inside minus a half a half?
It's going to be inside the circle. It's less than 1.
Well, our first problem is that 11/14 is not inside a half. 7/14 is the halfway point, and we have 11/14. So
Less than half.
yeah, so we're between a half and 1. So 11/14 is here somewhere.
So we gotta translate it to
Yes,
less than half.
yes, we have to translate first. Let's see, let me draw this unit circle. That's supposed to be a unit circle, and here's our minus a half. 11/14, and then what's the roughly the size? What's root 19 over 14? Gosh, root 19 is about 4. 4 over 14, I don't know, a third-ish. So it's somewhere down here. It's a pretty small.
0.31 or something.
Yeah. Okay. So this is our alpha. This is our original alpha. Alpha sub q. Does everybody see that? All right. So the first thing I want to do,
It's translated.
translate. Forward or back?
Back.
Back. So that's t inverse of the original alpha, and that gives me the point. So I'm going to subtract 1 from here. So I'm subtracting 14/14.
There's gonna be -3 over 4.
Minus 3/14 plus root 19 over 14. I. So that's here somewhere. Minus 3/14. We're inside minus a half, so now we're happy. But we're quite clearly inside the unit circle, so we're unhappy.
So we have to flip it outside the circle.
Let's call that S.
Okay, alpha 1.
So that's -1 over -3.
-3 over 14 plus 19 over 14i.
Perfect.
Multiplied by the conjugate of that, which is -3 over 14 minus minus the negative root 19 over 14i to the denominator as well. -3 over 14 minus.
Beautiful. Okay, keep going. So let's fix the numerator first. So that's pretty easy. 3/14 plus root 19/14 I.
Yeah.
Well, we have to work out the denominator. Gosh, 3 squared over 14 squared.
Big one.
9, 14 squared, 196.
Yeah.
And then it's a difference of squares, so that makes it easy. It's just a plus sign because I squared is -1, so it's minus. And then this is 19 over 196. Actually, it's not so bad.
Yeah, it's 28 over 196.
Yep, 28 over 196. So that means I want to multiply top and bottom
2 over.
by 196 over 19. Okay. Yes, so what does cancel out? The 3 over 19 and a 4. So I have 3 times 14 on top. 3 times 14. 3, right, these cancel and I just have a 14. 14 times 3 is 30, 42. So I have 42 19ths is the new real part. And how about my new imaginary part? 14 19ths. 14 19ths times root 19i. Did I do that right? Did everybody follow that alpha 2?
Yeah, that's correct.
Great. So where is that? 42 19ths, that's like over here between 2 and 3 or something. That's okay. That's okay, because we reflected, you see, we reflected all the way out here.
Yeah.
And where is 14 19ths times root 19? That's way bigger than 1.
Yeah, definitely.
Okay, so we reflected here and then here. Remember what S does. It reflects through the unit circle and then across the y-axis. So we're over here somewhere, alpha 2. So what do we want to do with alpha 2?
We gotta jump backwards.
We got to jump backwards. So if we apply T inverse to alpha 2, that'll take 19 19ths off. But actually we can right away take 2 of these off.
Yeah.
19 times 2 is
38.
38. So if we take 42 minus 38, 4 19ths plus 14 19, root 19, I. Okay, so that's our alpha 3. And where is this point? 4/19 is definitely between minus a half and a half. It's over here somewhere. And this is some big imaginary number. So there's our final answer, alpha 3,
Got it.
as simple as possible. Any questions? From anybody, not just Sheik. But check this out. If we put together what all of this was, so our reduced alpha 3 is t to the minus 2 s t inverse of alpha. Can everybody see that? So let's work out what this matrix is. This matrix, t to the minus 2, is translation by minus 2, which is exactly what this accomplishes. S is 0, 1, negative 1, 0. T inverse is this. Let's multiply out these matrices. This matrix multiplication is pretty easy. 0, 0, 1, negative 1, 1. Did I do that right? And so that times this, 1, negative 2, 0, 1, comes out to 0, 2. 1 minus 2 is negative 1. Hopefully you guys are doing this with me. 0 and negative 1, and 0 and 1. Okay, did everybody get this matrix? So what we've learned is that this reduced alpha 3 is equal to 2, negative 1, negative 1, 1 time composed with acting on alpha. So what is our reduced Q2? It's going to be our original Q1, or Q0 maybe, this 7, negative 11, 5 guy, composed with what? With this matrix? Remember the theorem, if you change the quadratic form by a gamma, the alpha is changed by gamma inverse. So we learned what the right gamma inverse is. That means we want to compose with, so that means this thing is gamma inverse. So we want to take the inverse of this to compose this form. And what is that inverse? So again, we switch the diagonals. We negate the off diagonals. Okay? So let's work out what that is. And then I'll give you your quiz. If you want to work it out, it's not so bad. Remember that the first part is Q of AC. This is going to be A2, B2, A2, B2, C2. And A2 is just Q1 of AC. And C2 is just Q1 of BD. You guys remember this? And B2 was some complicated formula, but thankfully we already needed it earlier. So we can call it. All right, so what is Q1 of AC? So Q1 is 7x squared minus 11xy plus 5y squared. AC is 1, 1. So I'm sticking in 1, 1, 1s for x's and y's. I get 12 minus 11, I just get 1. Everybody see that? Yeah, you could write Q1 as a matrix and do the matrix multiplication as well. Yep, that'll have exactly the same effect. Thanks, Dipendra. You can do exactly what we discussed with matrices. Since we're already here, let's just finish it off. C2 is Q1 of BD. So now BD is 1, 2. So this is 7 times 1 minus 11 times 1 times 2 plus 5 times 4. So what is that?
Gonna be
5.
5.
Beautiful. And now the midterm, the middle term, b2. So this is 2ab(a1), I'm just copying from here, plus ad plus bc(b1) plus 2cdc1. That's the b term. And what is it? A and B and C are all 1s. So A and B and C are all 1s, but not D. So this is 2 times A1 is 7, plus D. D is 2. 2 plus 1, that's 3, times B1 is negative 11. And a 2 CD. D is 2, and C1 is 5. So I have 14 plus 20, 34, and then 3 times 11 is negative 33. So 115. 115 is equivalent to 7, negative 11, 5, and I hope you agree that 115 is a simpler quadratic form. This is a reduced, I haven't given you the definition of reduced. This is a simpler quadratic form. All right, so let me give you the quiz problems. I'm really sorry we got rushed, but hopefully, so quiz problems. Quiz problem 1. Here's a quadratic form. Let Q equal, I don't know, 4, 3, and 2. That's a nice quadratic form. Its discriminant is 9 minus something. Okay, so this is going to have negative discriminant. Find alpha. So there are 3 parts. Find alpha, reduce alpha in the upper half plane, as we discussed, and C, use that reduction, use the reduction in part B to reduce Q.
So what does alpha belong to?
So alpha will be, alpha is the root of Q. Just like here, we got alpha. Alpha is negative B. Alpha is the root, negative B plus root D over 2A. Hopefully I haven't made it so simple that this already is reduced. Well, if it is, then you have an easy quiz. But I'm hoping this alpha will not be completely trivial to reduce.
So for the second part, it's
Here, let's make it really, let's make sure it's not trivial to reduce. There. 14, 3, 2. Because you're dividing by 2A. So, go ahead, Sheik.
so for part B, you saying reduce alpha into something. What is that?
Oh,
letter?
this H, this is a bold H, upper half plane.
Oh,
Upper half plane. This is just a subset of the complex plane.
okay.
Daniel, you were writing a question? In other words, do exactly what we just did. Just do exactly what we just did. We took a quadratic form, we took its root alpha, we manipulated it to find the reduced quadratic form, and then use that to reduce, find a reduced root, use the reduced root to find the quadratic form. So if the starting Q is already reduced, then does the reduction algorithm return Q? Yes, exactly, that is what it does. If this already is as simple as it can be, then the reduction algorithm returns it back to where it was. Should I give you one more of these? Let's do 2 of these. So quiz part 2, because once you get the hang of this, it gets really easy. It's literally like adding fractions or something. Let me give you the one that I originally wrote down. 4, 3, 2. Do A, B, and C the same. Okay, this one might actually be reduced, although, yeah, there's going to be a denominator with 8. because the denominator is 2a. So maybe this one's also not reduced. Okay, you have some work to do for both of these. Any questions?